So now we are going to understand the concept of unbiased estimation using Python, and here we will consider different distributions that we have studied so far one by one, and we are going to begin with the normal distribution. So let us first import the necessary libraries. Import NumPy as NP. So as you all are familiar with these libraries by now. So now we are going to import from scipy.stats module, we are going to import norm, because we are going to work with the normal distribution. Once we have imported this, now we want to ensure that the same sample is produced every time. So we will write np.random.seed 0 over here. So this line basically sets the random seeds to ensure reproducibility. Okay, you can, so here I have set it to 0. This is an arbitrary number over here. You can choose any non-negative integer. Okay, next we are going to set the true parameters of the normal distribution. So let us define true underscore mu, suppose this is 5, and true sigma as 2. So basically we are drawing a random sample from normal distribution with mean 5 and variance 4. So now let us generate a random sample. So let me just write a comment, generate a random sample from normal distribution. So for this, first of all, we have to mention the sample size. So sample, let us take it as 100, and then we are going to generate a random sample, and it will be stored in this data sample variable, data sample. So for this we are going to use norm.rv. This is a function which is provided by your scipy.stats norm module. So rvs, and then this is used for generating random numbers from normal distribution. Okay, so here we will specify LOC is basically your true mu that we have defined earlier as 5. Then scale would be your true sigma, and the size would be the same as the sample size. If you recall, these steps we have performed in the last week's lecture also, because we were drawing there also, we were drawing a random sample from a specified distribution, and then we saw what will be the maximum likelihood estimate or the method of moment estimator. So here we are going to see the concept of unbiased estimation, that the estimator that you have drawn, is it unbiased or not. Okay, so after specifying this, what happens is that this particular line over here, this data sample variable, this will contain an array of 100 random data points which are sampled from your normal distribution with the specified mean and standard deviation that we have defined over here. Okay, now we are going to calculate the moments, because in normal distribution we need sample mean and sample variance. So let us first find those. So sample underscore mean, this one would be again taken from your NumPy library. So we will use np.mean function. So here we would write data sample, which is basically storing the 100 random numbers that we have generated, and your sample variance would be again obtained using np.var function from NumPy. So again we can write this. In addition, let us find the length of the data set, although we know it is 100 only, so just to assign it, so we have this. Okay, so sample mean will contain this line over here, would contain the average of the data that we have obtained here. This would contain the sample variance, and this finally would calculate the sample size. Now you know that for method of moment estimator or your MLE, in both the cases your estimators were same. right? Mu hat was x bar, that is the sample mean, and sigma hat square, that came out as n minus 1 over n times s square, that is sample variance. So let us write that. So estimated mu was same as the sample mean that we have calculated, and estimated sigma squared, we can write, this one would be n minus 1 divided by n into your sample variance. Okay, so estimated mu basically would contain your sample mean, and this estimated sigma squared would be n minus 1 over n times sample variance. Next, we are going to generate multiple samples and estimate the parameters in order to find the expected values, because in an unbiased estimation we need expected value of x bar to be mu, right, or expected value of sample variance. So for that we need to generate multiple samples. So let me just write this comment: generate multiple samples and estimate parameters. So let us take that the number of samples that we would be taking is 1000. Okay, you can adjust this number as needed. And then estimated mu values, this would be np dot zeros num sample. So let me explain to you what is happening over here. So this line basically initializes an array called this estimated mu values with the length equal to the number of samples that we have taken as 1000. Okay, so it will be used to store the estimated means for each of the generated samples. Okay, initially it is assigned 0, so all the elements of this array are set to 0 initially, and then it will store the estimated means for each of the generated samples. Okay, so in this case we have taken it to be 1000. So one array is this, another array would be estimated sigma squared values. So again here we will use np dot zeros. So this won't be an e over here. np dot zeros, and here also we would write num underscore samples. Okay, so here again initially all the elements of this array would be 0, and then it would store the estimated variances for each of the generated sample. Okay, now we need to initiate a for loop that would generate multiple samples and estimate the parameters. Okay, so let me write over here for I in range num samples that we have already defined, so 1000 over here. Okay, so we are going to initiate a for loop that would iterate these many number of times. Okay, that is 1000. Now the data sample would be again your norm from normal distribution we are going to generate. So location would be your true mu, and scale would be true sigma, size would be your sample size. Okay, next we will have the sample mean. So sample mean would be using np dot mean function from here, and here we will write data sample. Okay, So it will calculate the sample mean of that particular sample that is being selected over here. For that sample, it will calculate the sample mean, and it will also calculate your sample variance. So we'll use np.var over here. So here also data sample, yes, and we will also specify the DDOF because we want it to work with your sample variance. Okay. Next we would write estimated underscore mu values. This would be sample mean. So here basically sample mean is the calculated sample mean for the current sample. Okay, so you have drawn, first of all you have drawn a random sample from this normal distribution. You have calculated mean and variance. Now once for that mean you have the mean that you have calculated, here it will be assigned to this estimated mu values to the ith element. Okay, because for that particular I, that mean would be assigned to the ith element of this array. Okay, it will store basically the estimate of the mean for the current sample, and likewise we will use estimated sigma squared values. Here also we would write I. So this one would be, so I can just copy this from here. Okay, so whatever sample variance has been calculated for this sample here, it will perform this step, and then it will be stored in this, it will be assigned to the ith element of this array. So this loop basically what it is doing is, it is generating multiple random samples over here. It is calculating the mean and variance for each of them, and then it is assigning, or these estimates are basically used to find the expected values. Okay, so these will be assigned to these corresponding arrays, and then now we are going to calculate the expected values. That is the expectation. Calculate the expected values. So expected, we have estimated mu values already, right? So estimated mu we have written, so we can write from here. So this one would be obtained using this function np.mean from NumPy library, and here we would have estimated mu values. Okay, so it calculates the average over here. Okay, so np.mean, it will calculate the average of the values in this particular array. Okay, and this array which you have expected estimated mu, this is an array that contains the estimated means for each of the sample. So you have obtained this. Likewise we will obtain expected this also. Expected underscore this, and again we will use np.mean of this because we are calculating expected values, expectation, that is on an average. So again we will use np.mean only. Okay, now we can print your expected values and your true mu's. So let us just print finally. So print if expected so let us use the same notation that we have used here. So expected value, I can write expected value of for mean So here we will use this one. Okay, and we will also print the true mu that we had initially. So true mu, true mu would be again obtained using this true mu that we have already assigned. Okay, so it is going to print your expected value, right? Expected value of x bar that is going to come over here, and your mu, initial mu that we had, that was 5. It is also going to print it. Okay, so we have used this f string over here. So first of all, these would be evaluated and then substituted for printing. Next, likewise, we could have print f. We will write expected mu value. I would write expected sigma value. Okay, and next would be your true sigma square. So this one would store your true sigma that we have defined initially. So we are squaring it up because we are now dealing with the variance, not the standard deviation. Okay. Yes. So mu was your 5 initially, and your expected value when you are taking the sample mean as the estimator for your population mean, and then for that you have calculated expected value of x bar, then what you have obtained is 5.002. So you can see that how close it is, and your expected sigma value, it is 3.936 as compared to 4 that you have obtained here. Okay, so you see that these are your unbiased estimators because they are very much close to your population parameter. So on an average, your expected values of the sample mean and the sample variances come out as same as your corresponding population mean and population variance. If we change over here, let us make it 2000 and then we rerun this. So let us see. So it will get closer to this. So it is 5.003 also. Okay. So this was for your normal distribution. Okay. So let me just write it. So the next distribution which we are going to study is your uniform distribution. Okay. So for uniform distribution, what are the libraries that we need? So we have already imported NumPy, so we can just rewrite it, no problem in that. Import NumPy as NP, and then from your scipy.stats import uniform, because we are going to deal with the uniform distribution. We will set the random seed. So np.random.seed. So you all know the role of this particular step, and we are going to assign the true parameter of the uniform distribution. So true parameter in this case, so let us take it as theta as 8. So basically we are dealing with uniform 0, 8. Okay. Now we are going to generate a sample from this. So sample size as 100. Again, the data sample, we are defining it. Data sample would contain uniform dot RVS. So location 0, okay. Scale would be theta from uniform 0,8 and size would be your sample size. Okay. Now you can calculate the sample moments. If we use here your method of moments, so in that case for your uniform estimator was point estimator. In case of the uniform distribution was twice of the sample mean. So let us see if the method of moment estimator is your unbiased estimator or not. So for that we need to first of all calculate the sample mean. Okay, so sample mean would be np dot mean function we will use, and we will write data sample over here. Okay, and your estimated theta over here would be twice of the sample mean. So now we will generate multiple samples from here. So this is how you generate a single sample. If you have to generate multiple samples from uniform, you have to define first of all the number of samples that you would be drawing. So num samples, suppose it is 1000, or you can say it as 10,000. Okay, and your estimated theta values, for this we are initializing an array whose all the elements are 0 initially. Okay, and it will have these many number of elements, that is num samples, 10,000 elements would be there. After this we are going to initiate the for loop for I in range of num samples. So data sample, maybe I can just copy these from here only, because this is for single sample. Okay, so we have obtained for single sample, now we are just showing it to you for 10,000 such samples, because we need to calculate the expected value. So for I in range num samples, data samples, uniform dot RVS, location and size are specified. So this is there, and estimated theta values here, it would be twice of the sample mean. Okay, so to the ith element of the array, this mean multiplied by 2 would be stored in at this particular position, ith position. Okay, now you can calculate the expected value for that. So expected estimated theta would be np dot mean of this, because we have to calculate the mean expected value. That means you can use these variables for storing, you can name them as per your need or whatever you are comfortable in. It's not necessary that you have to use the same terms that I am using over here. Now finally we can print it. So let us print if true theta would be the theta value that we have specified, and my estimated value, let us see what it is. So let me just for f expected theta okay. So this is true theta was 8 and expected theta that we have obtained, that is theta hat twice of the sample mean, it is 7.996. So maybe we can do a bit of formatting over here. We can take up till 4 decimal places only. So you will have 8.0020. Okay. So you can see that all these are your unbiased estimators. So we are done with your normal distribution, uniform distribution. So these were your continuous cases. We can now move on to the Poisson distribution and Bernoulli, which are your discrete cases. So let me write for Poisson distribution. So import NumPy as NP. So we need an NumPy library in all the cases, and from scipy.stats you need to import whatever distribution you are working with. Okay, so as in case of normal distribution we imported norm, and for uniform we imported uniform, and now in this case we will be importing Poisson. Okay, so np.random.seed, this one would be, let us set it to 0. Poisson has again a single parameter, so true lambda, let it be, that is lambda is 3 in this case. If you generate a random sample, then it would be simple. You can see how to generate a random sample. Generate a random sample from here. So the sample size, let us take as 100, and we are going to define this variable data sample that would store, basically random variables would be generated from your Poisson distribution with mean mu is given as the true mu, true lambda that we have defined, and the size would be the sample size. Okay, now you could again calculate the sample mean, because sample mean here np.mean, Poisson distribution lambda hat was sample mean, so we calculate that. Next, your estimated one was also estimated lambda, we can save as the sample mean only. Or maybe directly you could have written here estimated lambda and sample mean are same. Okay, so now you will generate multiple samples. Okay, from Poisson. So for this again we will define how many samples do we need. So let me just write 10,000 over here, and then we could write here estimated one. Okay, so estimated lambda values. So for this we are initializing an array over here, and so it will be num_san, these many elements it would store. Now, as we have seen, for generating multiple samples we need to initiate a for loop for I in range num_samples. So we can use this from here. Okay, so data sample would store your random sample that is generated from your Poisson distribution with parameter lambda, that is 3 over here. Sample size is given, and sample mean would be calculated for each of these sample. The sample that is drawn, you would calculate the mean, and then here let me just write estimated lambda values. So here to the ith position in that array we would assign your sample mean. Okay, so once it is done, you will have an array for estimated lambda values, and we can calculate the average of those so let me just write expected, because we are going to find now the expected value of this. So np dot mean okay, so if we just print this value over here, true lambda is not defined. Lambda, sorry, here it should be true, and here also it would be, the spelling of true was incorrect, sorry for that. Yes, so it comes out as 3.001831. So you could also restrict it to 4 decimal places if you want that. So you can see that these are all your unbiased estimators, and this is how your unbiased estimation works. It's a nice property for any estimator to have, and in the long run also, when you go to study about your statistical inference, and you will see various properties, so you will see that this one being the simplest one also, and it is very useful, we will end up with this unbiased property only. Obviously there will be more to it, because at the end we get uniformly minimum variance unbiased estimator. So among the class of the unbiased estimators, you are going to find the estimator which is having the minimum variance uniformly. Okay, so as we are not covering those topics, I am just giving you a hint of what is your unbiased estimation and how does it work. So this is for Poisson. So likewise you can do for your Bernoulli distribution also. It is in the same way. You are going to import the NumPy library, and from scipy.stats you will import here. You would be importing Bernoulli. Okay. You will define your true parameter, what it is. You will generate a random sample for this. And then finally you will generate multiple samples and calculate the expected value. So if you want, I can quickly write it for Bernoulli distribution. So let me just import NumPy as NP, and we are going to import from scipy.stats import Bernoulli. Okay, so np.random.seed would be 0, and then true p we would assign as 0.3. Okay, let us suppose this is the probability of success for us. If you generate a simple single samples of size 100, then you can draw a sample from Bernoulli.rvs. So we would write, because Bernoulli also has a single parameter, so we just need to specify that. Okay, the sample mean would be what? In this case we would use the np.mean function. And your estimated p would be the sample mean. Okay, so these are the steps, these same steps we are performing for Bernoulli. Okay, so now we can generate multiple samples. For that we will again be using this num samples. So let us, number of samples that we need, let us take it as 1000, 10,000 suppose, and estimated p-values. So we are initializing an array. So np.zeros, we will write num underscore samples. Okay, and for I in range we are initiating a for loop that will go through each of these samples. It will draw a Bernoulli sample, okay, with parameter p from each of these, and for each sample it will be calculating the sample mean, and finally it would be assigned to the ith element in this particular array. Okay. Finally, you would calculate your expected value. So what would be the expected value? So let me just write expected value would be np.mean of the estimated p-values. And let us see what is this expected value. Okay, so it should be a small letter b over here. Okay, that is why error was coming. So now it is 0.300519. Okay, so you can see that these are all your unbiased estimators. So we have looked at two cases from continuous distributions, that is uniform and normal, and two from your discrete families like Bernoulli and your Poisson distribution. Okay.